waiting for 2 students, but that's the time that we should start. Hopefully they can join us very soon. Today, I'm going to complete the development length and start the column. But the development length is part of the exam. The column is not. So deflection plus development length, these 2 chapters would be in our second exam. Most of the class, they sent me the homework for deflection. Still 3, 4, 5, 6, 7, 8, 9, 10 students. That's a lot. They didn't send that to me. So if you cannot solve that problem, you cannot actually get 50% of the exam. So let me make that completely clear. I start talking about this about 2 weeks ago, and I sent email to everybody. Please solve this example and then the homework, because I know those are important. Please do it. Next week is your second exam. If you cannot get good grade, if you had bad grade on the first one and you cannot get good grade for the second one, then that's your last chance. That's it. There is no more chance. Yeah. So please do it. I will help you try the best and go after reading the example. I got some emails that uh, the answer was not correct. So I'm not going to talk about those right now, because I need time for this lecture. During the homework, I will let you, and because of that, hopefully in the that part, one of the actually friends text me, Professor, which example was 50% of the exam? No, not example. The deflection. Deflection is one of the chapters. Yeah. So we have 2 chapters, just 2 chapters for second exam, just 2. Yeah. So each chapter has 50% of the exam. So if you know that development, if you know that part, is almost more than 50% chance, because deflection is more important. You have to have more knowledge rather than this the other part. And
Professor,
so you will get 50-50 almost. Yes.
I think I remember you saying that if we study your seventh lecture, then that should help us on development, like in that. So that will help us get 50% points on the exam.
Look at this. Each chapter is 50%,
Oh,
almost.
okay.
Yeah, because it's not 100%. We have 2 chapters. So if I give you 2 questions, should be one from that chapter, one from the development length. That's it. So if you cannot solve, for example, deflection, you will lose 50%. Yeah, just I want to make
Yeah.
that a little easy to understand, because it's 2 chapters. If we have more chapters, so the chance was less. But please, it's completely clear that you need these 2 chapters to get good grade. And I am sure that those that they work on them, this homework, and they solve the examples, please do not go after homework before you can solve the example. I got one actually answer completely wrong. He did a very good job. He went all the way through, but he forgot to use different Y bar at cracked and uncracked. So it's wrong, completely wrong. Yeah.
Okay.
Please solve the examples. Make sure that you understand that completely. If you have question, ask me. Then go and attack the homework. And in that case, you will get less mistakes or less problems. That's it. So I'm here to help. Go and read those, and then if you have question, ask me.
Okay.
Another chat. It is possible for you to post this lecture on Beachboard, so that it's easier to take. Sure, I can. Sure, I thought I did, but I mean, I'm too busy sometimes. So I have, let me do it right now. So you will see that very soon. So today, actually, I'm going to give you um, development length, how to use it. Yeah. So we know how to use it for those examples that I gave you, but it's not just for that. That's good for cutoff point. That is very important as well. So today we are going to actually learn how to use that part for this cutoff point. And that's a very important part of this actually development length. Okay,
Professor,
so yes,
will we be given all the ACI codes for the exam?
no, you have all the things that you have. Yeah, you should have them already. So you know what I mean? So
All
you
right.
have it already. I'm not going to give you anything else. You have all the slides, you have your book, so everything that you need, you should have it. Yeah.
And there are things from the first few lectures and the first test that we'll need to use for this one, correct?
May I ask you to repeat that one more time?
There are equations that we use in the first few lectures and the first test that we'll have to use for this upcoming test, correct?
All the equations that you need, yes, I told you from the start, please put all the equations on few pages. So whenever you need that, you don't need to go through the different actually slides to find them. Yeah. And because of that, I know that even at the end, you need something from actually A, calculate A, or find the moment capacity. Those are something that you need them always. So in that case, you should know how to actually find those, and you need those stuff. Yes, you need those equations, and please write them on something and make them clear based on the all the homeworks that or the examples. All the examples. Look at the examples. Whatever you can see on the examples, you need those equations. That's that easy. That's it. You don't need anything more. Yeah.
Okay. Mhm.
And please just let me know if you have any other question, and I will give you the answer for sure. So right now, that lecture, this lecture is on Beachboard. So if you want to go, please go, and you can see that. Okay, let me go and start this. Today, I add this part on this slide to make that more clear for everybody. Hopefully it will help. So in order to find the cutoff point, what's the cutoff point? Let me go through this. Consider that that's a columns, yeah, column, a beam. That's a elevation view for a connection between beam and column. And imagine on top, you have two continuous rebar number 10. Just I made that simple. Yeah. Two number 10. And we have one number 11. I show that two number 10, one number 11. That's section A. Yeah. I hope this will help us to understand this faster. And at the same time, at the bottom, you have two number 8 continuous. Yeah, two number 8. You can see two number 8. In section A, you have 3 bars on top, one at the bottom. When I show this here, doesn't mean that those are in 2 layers. Look at this. That's the only way we can show the length. So it means that this number 11 is not the whole length. We cut that somewhere. Yeah. So because of that, we are showing them in 2 layers. But in the cross section, it's something like that. Yeah. But if we cannot install those rebar in 2 layers, then we show like this, and then in cross section, we show those rebar at the second layer. But in this case, it means that all these 3 are at 1 layer, not 2. Okay. What about here? We have 2 continuous at the bottom, 1 additional on at the bottom. Yeah. And then on top, 2 number 8. So in this case, those 2 number 8 is here. One additional here is number 9. You can see it. So we have one number 9 to number 8, and to number 10 on top, this to number 10. Yeah, that's cross section B. Okay, so cutoff point, it means that whenever we don't need that rebar, we can cut it. So how can we find that location? We call that cutoff point. Look at this. And this is cutoff point for positive moment, cutoff point for positive moment, cutoff point negative moment, cutoff point for negative moment. The other one is continuous. We are not going to cut it, or this one is continuous. Okay, so how to cut this? The equations that we need are this MN, ASFY, that's the equation we need. How to calculate A? Based on the rebar, because we know the size of the rebar. We know two number 10 and two number 10 and one number 11, for example. So we know the rebar, yeah, and these are the capacity tension part, not for the compression. So over there for the tension part, yeah. So MNASFY, that's the equation from the past. That's the A equation. You should know this. And then based on A, you can find C. Beta 1, we know that based on F prime C. That's the equation we need to know. So we can calculate C. That's the neutral axis. C over dt, we can calculate that. And then based on that, we can calculate phi. So do I need to assume something for phi? No, because I know AS, I know F prime S, B, everything, so I can calculate A. A means C, C means phi. So if I can calculate this, there is no need to assume this. But if I don't know AS, so I can't calculate A, I can't calculate phi. So in that case, I have to assume something for phi. I hope it's completely clear. It's from the last two, actually chapters from the first exam. So in this case, for example, here for moment, look at this MN1. That's the MN1. This location. That's the maximum negative moment. What the phi MN1? That's negative. That's the capacity. Look at this. Capacity be a little more than the maximum negative moment or equal. Yeah, your capacity should be equal or greater than the moment. In positive moment, in negative moment, always should be equal or greater. So Mn from this equation. So Mn negative 1, based on this A and As that we have, we can calculate that Mn1 negative for two number 10 and one number 11. I can calculate As. I can calculate, based on the As that we have, I can calculate Mn negative 1. Yeah, that's the moment capacity, negative moment capacity at location 1. Yeah. So phi times that should be mu capacity. This mu should be greater than this moment. This is the moment diagram. How can we draw this? You should know that's from structure and analysis. Yeah. So in this class, I'm going to give you this moment diagram, so you have it. But in future, you have to plot this. Nobody is giving that to you. You are the engineer. You must provide them. Yeah. So in this case, we know the moment capacity, and that's the maximum moment based on the loading. Look at this. I put that this moment negative U1. It's here. That's from loading. That's from the capacity. How can we calculate this? That's the equation. Go and find M negative based on this AS, and A multiplied by phi. That's your capacity must be greater than or equal to this. Okay. So with this 3 rebar, you have capacity here. The moment is here. We are good. Then I know that, look at this. If I go this far, the moment is here, the moment capacity is here. So we can cut the rebar. We don't need to have all the rebar for the whole length, because over here, the moment, negative moment is 0. Then it will go to the positive side, all the way to the center. Yeah? Consider that's a center line of this. So up to here, the moment negative, it should be 0. Maximum negative moment from loading, all the way to 0 negative moment. Then the positive moment will be started. Maximum, then positive to 0, then negative for the other side. Yeah. So if we can solve everything on one side, the other side should be exactly the same as this. Do the same for the other side as well. Okay. So I want to cut this rebar. Which one? I want to cut number 11. Yeah. That one extra rebar that I put that here, I want to cut that because it's extra. So how can I find the location that I can cut that based on theory? If I cut that here, just assume that that's the location that we can cut. Yeah. This line is just right now based on, I assume that I am going to cut number 11 and this one is here. So how can I find this line? This line is the moment capacity for the remaining of the rebar. Is that correct? Because this one is for two number 10 plus one number 11. I want to cut the number 11. So in this case, I have just two number 10. Do the same as this, but your AS doesn't have this one. You have two number 10 only. So in this case, you will get MU negative for two number 10. That's it, this line. This MU negative, yeah, that it means that MN negative for two number 10 times phi. You will get MU negative. These are the capacity, yeah. Those are the capacity. This capacity should be for two number 10. How to calculate that? For two number 10, calculate A, C, phi, then put this A in this equation, find MN. MN times phi will give us the MU for two number 10. That's the line for two number 10. Yeah, based on the scale. If this one was 400 kip foot, and this one is for 300 foot kip, just based on the scale, you can draw this. Yeah, that's it. You don't need actually to do even by a scale because we have to calculate the length. So, and you will learn how to calculate that. So I hope I made that clear. Whenever you want to cut a rebar, you have to find the moment capacity for the remaining of the rebar. Like your remaining of the rebar are two number 10, 1, 11. We cut number 11, so the remaining is two number 10. Okay, what's the question?
Why did we cut the number 11 bar?
Because look at this. Uh, here with number 11, we are above the maximum moment. If we go here, the moment we need moment capacity here, or over here, moment capacity is this one. Over here, moment capacity for negative should be 0. So that's too much still if we go all the way to other side with two number 10 and one number 11. So we are going to cut the extra bar. Yeah, because it's too much. This is good for maximum MU1 negative. If I go this way, you can see the moment, negative moment will be reduced, 0. Over here, there is no negative moment. So we should have no negative rebar. Yeah, there is no negative moment. But in California, because of the earthquake, we must have 1/3 of the maximum rebar continuous. Yeah, at least 1/3. And because of that, we continue. But in example from the book, you can see there is no rebar on top. And I am solving that one as well. Is that clear for everybody?
And how come we don't include the two number 8 bars in our calculation for MN?
Because we are going to cut the tension bar only. Yeah. So the tension bar only are on top. We are not considering the compression bar to make it easy. No compression bar in your calculation. Just go with the tension bar. Yeah, make it easy. So that's easy. Okay. So everybody in the class, we need to understand this, that we have to go with the remaining of the rebar. Why? When we cut the number 11, we have those number 10. So this is the moment capacity after this for two number 10. We are going to cut one of them, one number 11. The rest should be for two number 10. Just remember, whenever you cut any bar, you must calculate the moment capacity for the remaining of the bar, not for the one that you cut it. Yeah, that's the rule. If you make that mistake and find for the other one, everything is wrong. Okay, so in this case, as you can see, we can calculate mu -1 from loading. As you can see, the moment capacity, yeah, is phi times this is a ultimate moment capacity. I put this, look at this. That's green one. This is green one. This is phi mn means mu. So mu from capacity must be greater than mu from loading. This is mu from loading. As you can see, this is mu. Mu from capacity is more. So zero moment negative, maximum negative moment from loading, and that's your moment capacity negative from the material that we used. Yeah, that's it. Hopefully this is clear for you guys. I'm sure it's not, sometimes it's not that easy, but if you follow the stuff that I told you, hopefully it should be easy for you to understand and be able to solve the problem. So then if we cut one number 11, as I mentioned, we have to find the moment capacity for the remaining of the bar, mean to number 10. As you can see, to number 10, I put this red line. That's the how to calculate this. For to number 10, you know the AS. Go to this, find A, find C, C over DT. I showed everything here. This is one layer, so D is equal DT, yeah, for top bar, because tension on the top for negative moment. So you can calculate phi, then find MN for to number 10, and with this A, then phi times MN will give you remaining rebar moment capacity, negative moment capacity, like this red one. That's the line. Yeah. So it means that based on theory, at this point, I don't need number 11 because the moment is going down and the moment capacity is more than that moment. Just try to understand this diagram. This diagram is helping us. This is the moment capacity. Over here, the moment required moment is this one, less than this. So to number 10 is good. Over here is zero, no negative moment, and still I have to number 10. That side I have positive, so I don't need any negative moment rebar, but still I have that. And for the positive moment, I should do the same based on the bottom rebar. So I'm going to cut one number 11, number 9. I have to find the MN for two number 8. Then find C, phi, and CMN. And based on this, I can find the moment capacity, some line like this instead of this line. This is for two number 10. For the here, two number 8 is here, for example. Two number 8 plus one number 9 is should be greater than mu max for positive. So that line is somewhere around here for two number 8 plus one number 9. For two number 8 is less than this. So this point is a cutoff point for number 9 based on the theory. That side based on the theory. But are we going to cut at that point? No, the code will not allow us. There are some codes that we have to find that and then extend that a little bit. So this part, I put that together to make that a little clear. And we will go after this to see the ACI rules for this actually cutoff point. Okay, back again to what we got from the, yes.
I have a question regarding last
Yes.
slide.
Okay.
When you say capacity, the capacity mu is larger or equal to mu from loading?
That's correct.
Oh, what's the difference between mu and mu from loading?
Look at this. Mu from loading, you calculate, for example, you have a simply supported beam with omega on top. So your mu positive should be omega u L squared divided by 8. Yeah, that's your mu from loading. Omega means omega u. That's loading. Yeah, uniform load times L squared divided by 8. That's the moment caused by the loading. And then we calculate this mu based on phi mn and mn based on the material. Look at this. There is no loading on this calculation. These are just the material. We call that capacity based on the material. Yeah. So this is provided. That's required. That's based on the loading required. This is based on the material provided. always provided must be greater than required. Both of them are you, but one of them is came from the loading, another one is coming from the material. Did I give you the answer?
Yes, sir.
Okay.
And
Thank you.
you will be giving us the required moment capacity, correct?
That's correct. That's correct. This part, I will give you the moment diagram. So you have the information from the loading. Then you have to come up with the other stuff that you need based on the material. Clear?
Clear.
Clear.
Okay.
Would we have to like show where on the line like that second MU would come in where we take out a bar?
Yeah, you don't need for the first one, just I show that just to let you know that based on the rebar that you have, it should be more than or equal the required negative moment. This one, you don't need that. But the second one, yes. And you can see right now in the example and the other parts that I'm giving you, how to come up with this and find this point. This point is important for us. Yeah, we will learn this. Okay, this is the code. What's the code? Is a cutoff point for, look at this. This is exactly the same as the one that I showed you. But right now with that diagram that I showed you, I think absorbing this is easier. This is the moment diagram. Yeah, negative based on the loading, maximum positive based on the loading. Sometimes in different books, they are using negative on top, positive at the bottom. Doesn't matter. Yeah. So the negative, they can show it on top, positive at the bottom, or negative at the bottom, positive, doesn't matter. The same actually regulation for negative and positive. So at first, at this side, I call them, look at this, I call this rebar L. As you can see, rebar L, cutoff point for rebar L. This L is here. This cross section is at this point. Yeah, we have two number M bar M's. Look at this. This cross section is here. This cross section is here. That cross section is there. So each one is at the location that you can see. Over here, you have three bars, bars M and bar L. Bars M and bar L. Bar M, over here, we cut this bar L. There is no bar L. For the bottom bar O, at the bottom, we have two bar O. Look at it, these are bar O. And bar O, still we have it. On top, we don't have L because we cut that. Over here, there is no top bar. There is no compression bar. We have three bars, bar N, one at the middle, and two bar O. Yeah, that's the cross section. So, and we are going to find the cutoff point for bar L at negative side. That's the first part. We are going to find the cutoff point for bar L. So what should we do? We have to find the moment capacity based on the remaining of the rebar, means 2 bar M. Yeah, because remaining is 2 bar M. We cut the green part and the remaining is 2 bar M. So I wrote that AS 2M for 2M. 1, 2, 2M. See whatever we have, AS for that one times Fy is, and calculate A and then find C, then find Phi. The same as I mentioned over there, yeah? So then calculate Mu2M, yeah? Should be Phi times A, and this part is Mn. Phi times that will give us the Mu2M based on the material. This is the capacity, yeah? So this is the capacity based on the remaining bars, and I wrote that again, bars M. Okay, M2UM, look at this, that's the line. M2UM, based on Mu2M, Mu2M. That's it. I showed this line. It means that I can cut based on the theory, this L, I can cut this here. Because can I cut this at this point? No, because you can see the moment is bigger than M2UM. Moment here is here, M2UM is there. Can I cut that L here? No, because the moment is bigger than capacity of 2M. But after this, can I cut that actually there? Yes, because 2m is greater than this. Yeah. So based on the theory, that's the point that we don't need 1L, because 2 number m rebar can tolerate this much of the moment, exactly this point. So before this, no, not good. After that, yes, 2 number 10 is good, because that is less than the capacity of 2 number 10. That's the based on the theory. How can I calculate this point? I need to know this. Okay. In order to calculate this, this is the diagram I showed you on the shear calculations. Exactly the same. Statics. Yeah, statics. You need this all the way to PhD. You must know these stuff, connect your information, use them whenever you need that. So how can I use that? I know the reaction. Yeah, you know the reaction of the beam. Yeah, we can calculate that based on the moment and loading that we have. You can calculate, you can remember that from the shear diagram. Based on the moment, you have to find the reaction. Then this is the X that I want to use this here. Okay. This is mu negative, because this is mu negative. Look at this. That's your mu negative at this point. That's mu negative. Negative, tension on top, compression at bottom. So always negative will go this way. And omega u, we know that based on the loading. At distance x, the moment should be what? The moment should be m2u. Look at this. At the x, what's this moment on this diagram? What's this moment here? I know that this moment is equal this, because at the same location. What's that moment? I don't know. I have to calculate that. That moment, I have to calculate that. But over here, I know that because it's equal to mu to m. So on this point, I know the negative moment. Is that positive moment or negative? Negative, 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 0. And then positive. So all the way to here, any moment should be negative. So I know moment here should be mu to m negative. I put this negative. What does it mean? It means that always should be at this direction. Tension on top, compression at bottom. If you consider that the opposite direction and write the equation, you will get wrong answer. And it means that you have problem with the basics. Just remember, anything that has to do with the basics, I'm not going to accept. If you make mistake by 2 by 3, you wrote 7, I will just reduce a little bit of the point. But if you miss something like that, that's a big mistake. That's a basic. Negative moment this side, negative moment the other side. Look at it. Looks they are opposite direction, but both of them are tension top, tension top. You come this way, tension top. Okay. Based on this, write sigma moment equals 0 at this point, or any point, but I will go at this point. Yeah. Sigma moment equals 0 if this direction is positive. Okay. I will start with this. This one is opposite direction. I will get negative mu1. Yeah. This mu1 is this moment based on the loading. Then this reaction will create moment at this point times x at this direction, the same direction, positive, or u times x. Then omega u, total this force should be omega u times x, and distance from here to here is x over 2. Yeah, that's it. So omega u times x will give us the total times this distance to this point for the arm, x divided by 2, and it should be opposite direction. That direction, it will go opposite direction. Negative omega u times x divided by 2. So we will get omega u x squared divided by 2. Then we have another moment that's at the positive direction plus mu to m equals 0. We know everything. We know this number. We know omega u. We know ru. We know m2u. How? We calculated that based on the rebar 2m. Yeah. So, and the only unknown is x. Find x. And you can see it's a quadratic equation. You will get 2 answers. So one of them is for the other side. Another one is shorter, is for this side. If you get 2 feet and 14 feet, 14 is for the other side if it's exactly symmetric. The moment diagram is symmetric. So it will give you X for this side and that side. This X and X from other side of this negative moment. So always go with the smallest one. Yes, what's the question?
Yeah, so if we said the moment was positive counterclockwise, could we still get the same answer?
And look at this, counterclockwise, this is not the answer. Look at this. This is counterclockwise. This side is clockwise. Both of them are negative.
Yeah,
Let's
but you also
remember.
said mu. You said positive mu2m. Wouldn't that be negative mu2m?
No. Look at this. That's the negative moment. But because I wrote that sigma moment at this direction, I will consider positive. So this one is at the same direction. So I will go with positive.
Yeah, so I'm just saying, like, if we changed it as counterclockwise was positive and we said plus mu1 and then negative mu2m, would we still come out with the same answer?
No, if you change this direction from a start and then rewrite this, then you will get the same answer. But if you go with this and go with half of them with this direction and then negative for this one, you will get wrong answer. Yeah, and because of that, I showed this. Always consider one direction for yourself from a start positive. You can go opposite direction positive, doesn't matter. But stay with that all the way to the end. So based on this, see, this moment will create a positive or negative around this point. So based on this one, it will negative because it's go to the left, but we consider to the right positive. So we consider negative. RU around this one will give us at to the right, so we consider that positive. Omega U will create moment to the left, we will consider that negative. Omega U2 will go at to the right, the same, we consider that positive. So it depends on what you consider. You have to find the direction based on this with positive and negative. Opposite direction, negative. The same direction, positive. Did I make that clear?
Yes, thank you.
Okay. Any other question?
Yeah, I have one more.
Yes.
For the MU one, is it the theoretical? I mean, like, is it the material one or is it the loading one?
Look at this. This is MU1 at the start. That's based on the loading. If from the material I show that with 2M or something, yeah, this is based on two bars M, yeah, that's the moment capacity based on the material. This one is moment based on the loading. That's MU1 is here, maximum MU. That's this point is here. RU reaction is here. RU and MU1, negative moment, RU1. Is that clear?
It's
Okay. Any other question? Okay. So based on this, as I mentioned, you have two answers. The smallest one is your answer. If you have negative, negative is not the answer. Yeah. So we calculated X. X is theoretical, actually location of the cutoff point based on the theory. You can cut this based on the theory, one number even here. But the code tell us, no, it's not acceptable because we have a lot of other material for factor of safety, incumbency in the material. We are using FRMC, the rebar, some problem in the FY. So the code will ask us to do something else. What? These are the actually things that we must to do. Theoretical cutoff point for L is here. Yeah, that's based on the theory. Then code asks us, you have to look at this, that's based on the theory. We can cut this L here. Code asks us, no, extend that the maximum of these two, D or 12 times the rebar that you are going to cut, means L, not M. Rebar, that's DB for the rebar that you want to cut, that's L. Yeah, this bar I am going to cut. Just remember, if you are using wrong dimension diameter of this, that's wrong. You have to go with the one that you want to cut. This is for what's the D? I showed that this, yeah, that you know D for each beam. Maximum of D or dB. Extend that from here. So from face of the column, you can go X plus maximum of these two. Find the maximum, add that to this. That's your cutoff point. Is that all? No. Then we need to check minimum actually extension or development length for number L for a straight bar means LD. So right now we have to back to development length, and for a straight bar calculate that if it's epoxy top bars or what, all of the stuff that you know. So calculate LD from face of the support, then X from here to here is X plus maximum of those two. You have one length there, one length LD. Between these two, yeah, do I need to actually go with the reduction factor? No reduction factor. So between X plus maximum of those and LD, pick the maximum. For example, X plus that one, you will get 25 inches. LD, you calculate that 30 inches. So your cutoff point is 30 inches from face of the column. That's it. Yeah. So the hardest part was finding X, then maximum of these two plus X, compare that with LD for a straight bar. That's it. That's the cutoff point. In this case, they ask if they want to cut the whole rebar. Look at this. Over here is positive moment. There is no need for the negative bar. Over here is 0. Maximum negative moment, mu1 negative, 0 negative moment. So for sure, we don't need any tension bar on top. So we can cut it, but not in location that we have high risk earthquake. Yeah, but imagine you are not in that case. At least we can learn. For this one, we have another case. So it's better this one as well. So how can we do that? We have to go and find the location that is, that's the theoretical location of cutting 2M. Yeah, I'm going to cut 2M. Then what should I do? Like before, find the capacity of the moment for the remaining of the bar. So if I cut 2M's there, what's the remaining bar?
0.
I'm asking you. 0, perfect. Look at this. Remaining bar, nothing. If I cut the L, what's the remaining 2M? If I cut the 2M, what's the remaining? 0, nothing. So do I need to calculate that? No. Moment 0 is your moment capacity, mu0. mu2M, one is mu0, means that there is no moment rebar, and because of that, the moment capacity is 0. How can I find this distance? Bear with this. How can I find this distance x1? If I call this x1, how can I find this distance? You should know, based on what we actually learned so far. How can I find this distance x1?
Do static.
So should I go with what equation on this slide?
The last one. The bottom
This
one?
one.
Yeah.
That's what. So what should I consider instead of this?
0.
0.
0, that's it, you got it, because there is no rebar, yeah? mu2m is mu0, means 0, there is no rebar. So mu is, so use the same equation, but this moment should be 0. Then this x should be from face to that point. At any point, if you know the moment, go to this equation for negative moment, this direction. If you want to find on that one, this is your positive. Yeah, so you should show this at opposite direction. Positive moment, negative moment, positive moment. Then you can find x. That's it. That's that easy. Is that clear?
Yes, sir.
Perfect. So in that case, this point is known. I know that point. Then the code will ask us, okay, that's based on the theory. You can cut all the top rebar. Yeah, 1L first, then 2M. It means that all the top rebar. You can cut that based on the theory, but based on the code, you have to extend that greatest of D and 12 dB. What's dB for M? Because we are going to cut M. dB for M or D, 12 dB or D. Extend that from here, that one. Or another one is you have to extend that ln divided by 16. What's the ln? ln face to face of the column. Length, calculate that, times 12. That's your ln, divided by 16. Yeah, the greatest of that one, dB, 12 dB, and ln divided by 16. Calculate those three. Pick the maximum plus distance actually from here to here. We know x. What's the distance from here here? I know x1, for example. X1 minus x will give us this distance. Yeah. X1 minus x will give us between these two. Okay. This maximum plus the result of x1 minus x, actually x1 minus x, you can calculate this, plus this maximum of these three, that's the total length. Then find LD for M. Look at this. You have to compare that new length with LD for M, because we are going to cut the LM. A straight development length for top bar, that's the top bar, yeah? Based on if you have more than 12-inch or not, if it's epoxy coated or not, all those stuff. Then see which one is greater. For example, this distance plus maximum of those, you will get 33. Your LD, you will get 30. So you should go with 33. So that's the cutoff point for 2M. That's it. As you can see, this for negative, that's for the total negative you are going to cut. If you have 4 rebar and you want to cut one by one, then you have another line here. Find the remaining of the rebar, go to this chart, find that X. As you can see, it's just doing the same as, but the one after the first cut will be considered from the theoretical cutoff point. Just look at this diagram, try to understand this diagram. Everything after this will be considered the theoretical cutoff point for the first cut. Then if you have another one, then go with this for the other cut. Theoretical, that's it. Yeah, these are just 2 examples, but you can use it for if you have 10 cuts, go one by one. Follow the instruction based on this. Yeah, one by one. Go with this situation, you can solve the problem. What's the positive? If I want to cut the positive rebar, as you can see, I want to cut the N. That's the N bar. I want to cut that. At first, I have to find the theoretical cutoff point. How can I find that? What's the remaining if I cut this? If I remove this, the remaining should be 2 number 10, 2 O's. Yeah, those are 2 O. So find those 2 O actually moment capacity, the same as this. Find A, find C, find phi, AS for 2O. That's the moment capacity, MU for 2O, times phi means moment capacity for 2O. That's it. Yeah, that's the moment capacity for this one. So, and as soon as you find this point, yeah, then for the cutoff point, go D plus 12 dB maximum of these two, D or 12 dB. What dB? dB for the one that you want to cut. And that's based on the theory. Let me answer the chat. So is phi still equal to, no, it's not 0.9. You have to calculate that even here. Yeah, we have to calculate. You have to find A, you have to find C. C over dt, go to the equation, find phi. If it's more than 9.9, consider 0.9. If it's less than 0.65, consider 6.65. Yeah, all the regulations that you know. Did I give you the answer?
Yes.
Okay. So then you have to do another thing, like is find actually this length from the maximum moment. Yeah. So you have to calculate this distance from here to here plus d or 12 dB. Compare that with LD. LD for what? For this bar that you want to cut. N. Go to the straight development length for bottom bar, this one. There is no 12-inch of the concrete above that, below this. Yeah. So just don't forget this, that part. Follow the instruction for development length. And this LD, compare that with this length plot D plus DB. See which one is greater. So see, find the maximum and then cut that at that point. This is the cutoff point for positive moment, for positive rebar. Yeah, as you can see, almost the same regulation, except this one that you are going to cut all the rebar. It has 3 parts: D, 12 dB, ln divided by 16. But when you are cutting 1 or 2, not the whole rebar, just always D 12 dB, compare that with LD. D 12 dB, compare that with LD. That's it. Any question?
I have one question.
Sure.
The second development length
Yeah.
For 2M, yes.
Yeah.
Why does it start at X but not at the face of the column?
Look at this. Because up to here, we need 2M. So from here, we need 2M. If we go here, we need 2M plus 1L. So you shouldn't compare that with this one. You should go compare that with 2M. Because 2M you are going to actually cut. So the start of the 2M is here. Here you have 2M plus L. So always you go with the one that you cut. The rest of the rebar will go here. So if I cut another one here, then you should consider that for the rest of the rebar as your base for the measurement. I hope I made that completely clear. Is that clear now?
Still a little bit. I'm not really clear.
One more time. Look at this. For LD, if when I cut number L, this L, it means that our start of 2M only is here, not here. This is the start of 2M and L. Here is a start of 2M only. And because I am going to cut the 2M only, LD must be considered from here, not from there. Yeah.
Then we consider cutoff point for L is a little bit extra comparing to X, and that's also have L. Yeah, that D or 12 dB, that's the extra for L.
That's correct. Because look at this. That's X, we need this L, because over here, that's based on the theory. Based on the theory, we can cut L. But code will ask us, no, do not stop there. Extend that maximum of these two as well. Then compare that with the total L, because L will be started from here. Yeah, that's the start of the L. And because of that, we compare that from here. Then 2M started from here. Over here, 2M plus L. Over here, 2M only. L is started from here. So we have to find the development length here shouldn't be less than theoretical cut plus the extension based on the code. Yeah, we extend that based on the code. Based on the theory, we can cut L here. But we are extending that based on the test that we did in ACI. So we are extending all the way here, but it shouldn't be less than the minimum required development length for tension. Yeah, we know that. And because of that, we compare this with the cutoff, theoretical cutoff point plus AC extension. And over here, we did that the same. Development length, that's the cutoff point based on the theory plus extension based on the code. Is that clear?
I think I see it now. Thank you, sir.
Okay. So let's go. I hope the rest that they are not asking question. It's not that actually hard, and they are following me. Yeah, and because your friends asking question, maybe those are your questions as well. So that's good. Yeah, kind of a teamwork. Somebody asks question, it's a lot of other students that have the same questions. So this part is the basis of ACI, if you can cut the rebar or not. One of these must be existed if you can cut the bar. Those are important. I will go just with this one. The others are not that easy, so it's not part of actually the things that you want. But if you have this case, that's good enough. The shear is not over 2/3 of the design strength, then you can cut the bar. So what does it mean? I want to cut this bar over here. Yeah. So based on that code, you know the shear diagram. Let me plot the shear diagram over here. That's the shear diagram. Just assume that. That's the shear diagram. Okay. Shear at the end of here. Look at this. This shear. So that's your reaction, RU. That's your shear at the cutoff point of L, for example. This shear shouldn't be, let me go to this page. I have to get out, otherwise I can't do that. The shear is not over 2/3 of the design strength phi-Vn. What's phi-Vn? Phi-Vn was equal phi-VSR plus phi-VC. Phi-VC was from concrete. Phi-VSR was from stirrups. Yeah. So this one should be less than 2/3 of phi-VC, phi-Vn. So calculate the shear capacity based on the spacing of the stirrups and VC, add them together times phi, 2/3 of that, compare with this. If this one is less than that, you can cut this bar. If it's more than that, you cannot cut this bar here. Maybe you can cut that here. So that's another thing. We have all this. There is another regulation here as well. Yeah. So just pay attention to this. I'm not going to actually give that in exam. I'm not going to ask you to check this one because you have to go through shear diagram and find all those stuff. I will consider that part is hopefully you know that because it's not that's strength structural analysis to go through all those shear and others. So, but just please remember, and because of that, I put this in a box for you guys in future. Whenever you want to find the cutoff point, just remember that there is some code and come to this slide or in the book or ACI and find it. And remember, 50% of your knowledge is to know what you can find the stuff that you need. That's 50% of your knowledge. It means that you don't need to remember everything, to memorize everything. We can't do that. But you can remember that there is something in ACI or somewhere that has some requirement for cutoff point. That's your knowledge. Go to that part and find it and read it. Yeah. Then the next day, forget it. Yeah. Whenever you need it, to again do the same. Remember that there is something. Go to the source, and then that's your knowledge. 50% of the knowledge is to know where you can find the answer. The rest of that 50 is your brain. You can remember that. Okay. Let's go and do example. I think with this example, you can see the answers. Hopefully. Find cutoff point for one number 5 negative bar. Look at this. We have 4 number 5, and I want to cut one of them. I want to find one, go through this completely and learn this completely. For the positive moment cutoff point, it's not as easy as this one. Yeah, it's not as easy as this one. If you can learn this, I'm happy with you guys. In other words, for the positive moment, I'm not going to give you any question for positive. Yeah, I want to just show you that I want you to learn and good get good grade. So just try to completely understand this. You can do this as well, but this one for sure you need, for sure. Okay, I'm gonna cut one number 5 out of 4. So what should I do? I know everything. Look at this. I know mu1 negative. Yeah, I know this. I know RU. Look at this. mu1 negative 93 point. I know RU reaction. I know omega U on the beam. I know D 17.5 F prime CFY. Everything that we need. No epoxy coated bar. Normal concrete. Why did I give you? Because we know that for LD. Okay. Your H is 20. I want to cut one rebar. I want to find the cutoff point for one number 5 negative moment. One number 5, this green one. What should I
Professor,
do? Yes.
so the number before the number sign, like for number 5, that shows how many rebars are in that section.
You mean this 4?
Yeah.
Yeah. This 4 means for number 5 to
Okay.
number 4. You can see. Yeah. Yeah. Whenever I show something like this, I'm showing that how many number 5 do we have. Okay.
Okay.
So over here, we want to cut one number 5. Yeah. And the DB is this one. Your AS is this one. Yeah. So the remaining of the bar, I have to find the capacity of remaining of the bar. When I remove this, 3 number 5. Each number 5 is 0.31. 3 is remaining. Yeah. So I wrote that mu for 3 number 5. This is capacity. Okay. 3 number 5. A is equal ASF5. I know B, I know everything. Yeah. B 10 inches and F prime C 4 KSI. So I can calculate 1.64. Then your beta 1 is 0.85 based on F prime C, and C is equal A divided by beta 1. And D is equal DT because it's one layer. D is equal DT7. And based on C over DT, if I calculate this, phi should be 2.5. It's not acceptable. Should be less than or equal 0.9. So phi is equal 0.9. And mu should be a point, should be phi times this equation. That's ASFI times D minus A over 2 divided by 12, convert to keep in foot. Yeah. So phi times mn, this is mn, divided by 12, convert to feet. At the end, I will get 69.81 foot kip. That's the moment capacity for the remaining of the bar. Look at this, 69.81. I don't need to calculate for the total rebar. You don't need that. I show that to show the meaning of that. So mu for 3 number 5, mu for 3 number 5, that's negative. Yeah, I didn't show that negative over here as well because we are at the negative part of this. So that's the moment capacity for the remaining of the bar. It means that at this point, I can cut number 5, one number 5, because remaining is more than the rest of the negative moment. So I can cut, that's the theoretical cutoff point for one number 5. Yeah, everything is here. How can I calculate this X? That's it. mu negative 1, mu negative for 3 number 5 at the right directions, omega u, ru, that's X. At this direction positive, follow the instruction, plug in the numbers, you will get this equation in the power 2. You will get two numbers. Look at this, 14.34 and 0.66. Which one is the answer? This is not the answer, yeah? Because this one will give us for other side. If it's a symmetric, so you will get X this side, X from face of the other column to this side, yeah? So from here, not from other side, from here to that point. Let me plot this. I want to make sure that you got it completely. We don't need that, but if it's completely actually uh, symmetric, imagine you have symmetric and you want to cut one rebar, number 5 here, one number 5 here. So you don't need to do this twice when it's symmetric. So you got 14, you got, that's the moment capacity for tree number 5. Just imagine these are the same, yeah? Then your X is this one. This is one of your X's. Another X is from here to here. So this 14.34 is from this face to here, yeah? It means that if it's symmetric, this distance is exactly equal this. If you calculate this, you will get the same. But these two numbers is one for here, another for the other side if it's a symmetric, yeah? But if it's symmetric, you can use it. If it's not symmetric, no, just use the one that is the smaller. Is that clear for everybody?
Yeah.
The quadratic equation you have, did you get that from the moment FBD?
No, from here, from this equation. From this equation, plug in the number mu1. You shouldn't consider this, whatever it is, 93.45 times negative. Because this negative is not because that's a negative moment. No, it's because of the direction that we consider for positive, we put negative. Otherwise, all the moments and everything here should be positive. But when we go to this equation, this direction, then it will get signs. Remember, it's very important. So this negative is not because the moment is negative. It's because this negative moment is opposite direction that we consider positive. And because of that, it got negative. Plug in all these numbers in this equation: RU, MU, omega U5, MU for tree number 5 is 69.81, and it's positive. Positive this one. Negative to 93.45, positive 37.5, and omega U negative 5, because negative based on the sign. In this equation, if you rewrite that, you will get this. And everything is number except x2 and x. So that's the quadratic equation. Solve it, you will get these two numbers.
If we take the moment from the support reaction,
No, from here. Why I'm taking this? Look at this. Otherwise, it's a good question. Please pay attention, because these are not the total force that I showed. We have another shear force here. If I go here, I have to calculate this shear, I will get the same answer. But if I take moment here, I have to consider this shear force as well. This shear force times this distance will give us another force. So it should be longer. And because of that, I will take moment at this point. So this force cannot create any moment if I take moment here. Did I give you the answer?
Yes.
I'm wondering how you solve mu1 for when you're summing all the moments. Yeah, that.
Okay, why? What's your question?
How did you solve for that? Like when we're summing the moments equaling to 0?
Yeah, look at it. Solving this one, look at it. Just look at this equation, this actually diagram. I have moment at opposite direction of this. I will get negative mu1. Then this one positive. You got this, yeah?
Yeah, that makes sense. I'm wondering what value.
And must be equal 0. Then plug in the number. mu1 is 93.45. That's the number. Negative 93.45.
Oh, I didn't see that.
Then RU 37.5, 37.5 x times x. Omega U is 5, negative 5 times x2 divided by 2, plus mu for number 3, mu for tree number 5, 96.81. Everything is clear except x. Then you can write this equation. Clear?
Okay. So like in this, we're solving for x, and since there's like an x squared, we'll have two x values, and we have to choose the one that's either positive or the smaller one.
Yes, that's correct.
Okay.
That's correct.
I
Clear?
have a question.
Sure.
How did you solve for phi?
Phi is actually for actually a beam design for the first exam. Can you remember? We had C over dt. We had two equations for the phi. One based on epsilon s, another based on C over dt.
Yeah.
Yeah, just based on those two, C over dt, because you have these two, it's easier. Go with this and calculate phi.
Yeah,
Clear?
I got different number for phi.
So what did you consider for, looking like this? I'm not sure that you actually did something correct or not. Please let me complete this, because after this I have to complete the column. For that section, during the lab, I will review this with you.
Okay,
Yeah,
sure.
good,
Good.
perfect. So we calculated X, very good. So right now, X is 0.66 feet from here, 0.66. Then I have to extend that D or 12 dB. Okay, D or 12 dB. I have to extend that. I know those two. And also I have to calculate LD. LD for the one that you want to cut, means 1 number 5. That's the equation for LD. That's the size less than 7. Can you remember we had two equations for simplified method, less or over? If you have stirrups or not, we have stirrups, everything is clear. So this is the equation that we have to use. So phi t, that's the top rebar. Look at this. We have more than 12 inch of fresh concrete underneath. So it's 1.3. And it's no epoxy coated. So phi is equal 1. So we have everything. dB number 5. dB is 0.625. That's the diameter. Lambda normal concrete 1. Ephraim C 4,000, not 4. Square root of 4. No, square root of 4,000. 60,000 Fi. Calculate this. You will get 30.82. Then I have to extend this maximum of D or 12 dB. D is 17.5. Yeah, this D was 17.5. That's our D. Maximum of D or 12 times dB, diameter of the one number 5. 0.6. Maximum of these two is 17.5. Yeah. So from here, we should go X plus maximum of those two and compare that with LD. X plus maximum of those two is 0.66 feet times 12, plus maximum of 17.5, 25.44. So based on the first one, we need to cut it at 25.42. If we calculate it, 30.83, more than that, or cutoff point should 31 inches. Just round it. So the cutoff point here should be at 1 inches from face of the column. Is that clear? No answer. I hope that's a good answer.
Professor, I have a question.
Sure.
I'm still kind of unsure what X2 is.
X2, look at this, is for other, you have two answers. Forget about what I mentioned. You have two answers.
Right.
One of them is 14 feet will go to other side of the positive moment. Look at this, will go to other side of the positive moment. That's wrong, because other side of the positive moment, you don't need negative moment. Negative moment up to here should be 0. Yeah, I think with this one, for sure, you can get it fast. So if something is other side of the, you will go to the positive moment. That's wrong. Stop it. You don't need that. Go with the one that is at the negative side, because you are finding this X should be between here and here. That's it. If it passes there, it's wrong. It's not your answer. It's not wrong. It's not the answer that you are looking for. Is that clear?
Okay.
Now, is that clear? I want to make sure that you got it and I gave you the answer that you want.
Okay, yeah, it makes sense. Because so from this equation, the negative 2.5x squared, you get 2x, right?
That's correct. You
14
will get
and
14 and the other
okay.
points is, yeah. So
And
this
you
one will pass the positive moment.
okay,
So
okay.
it's not the answer.
Okay, that was my
It should
question.
be inside the negative moment.
Okay, that makes sense.
Okay,
Thank
perfect.
you.
So
Professor, can you repeat
yes,
the last part before that question when we compare it to the LD?
look at this. We calculated that x from here, x plus maximum of those two, 25.42. And we calculated LD for one number 5, 30.83. Maximum of these two. So 30.83, more than that, you should go with the maximum of these two. X plus that, compare that with LD, go with the maximum. Between these two, this one is the maximum. We will go with 31 inches from face of the column. That's the final cutoff point for one number 5.
Okay, so X is the theoretical development length, but for
No,
code, we
theoretical, not development, theoretical cutoff point. Yeah, based on the theory, we don't need this anymore because from here, 3 number 5 and less, we need 3 number 5 based on the moment. Look at this, the moment capacity. Right after this, you need even less than 3 number 5 because moment is less than this one. So that's the theoretical cutoff point for one number 5.
and we
Did I
add
give you the
the
answer?
we add
We
the
add
D or because of
based
code.
on the code, they ask us not to cut that there, extend that, and then compare that with this, and then go with the maximum of those two.
Okay, I get it. Thank you.
All right.
And we
Okay,
converted our final answers for that into inches.
31 inches. Yeah, everything should be based on the inches because it's not that long. X, we got 0.66. Yeah, then we convert that to inches, 12 times 0.66. No. 12 times 0.66 for the X. Yeah, so X 12 times 0.66 plus 17 because that one is inches. This one is feet times 12 plus maximum of those two. That line above. Then we compare that with inches for this one, pick the maximum of those two. Clear?
Yeah.
Okay. So homework, this is not your homework. Actually, I'm going to change that. This is for positive moment. So it will take a long time. You have to remember everything from structural analysis to find the location of maximum moment, then go from that side, find a lot of stuff that is not part of this class. So I'm not going to spend time for that one. We have to cover reinforced concrete design. So if you want to do that, you are very welcome to do this. I put some note for you guys. Yeah, over here you can see, but it's up to you. You want to do that or not? But my question is, for this case, just find cutoff point for two number 5 negative. We want to cut 2 of them, not one by one. I want to cut 2 number 5 out of these 4. Do the same as this one. Find cutoff point for 2 number 5. That's
Professor?
your homework. Yes.
So in this problem where we had to find the cutoff point for one number 5,
Yeah.
would that mean our AS would be a different value than what it was?
That's correct. Because
Okay.
you are going to cut 2 number, your remaining bars should be 2 number 5 instead of 3 number 5.
So AS would be 0.62 inches squared?
0.62, that's correct. That's for remaining bar, yes.
Okay, and we just basically do the same thing, we'll just get a different...
Exactly do the same. I want you
Okay.
to repeat this, please. Solve this first, make sure that you can do it, you understand this, then go after that.
Okay.
Good. So
Yeah.
please forget about this homework. This is not your homework. Do that one. Just cut off point for 2 number 5 on top. That's it. Then another thing that we should know is lapis splice. Lapis splice, you need that a lot. You need this a lot. This is very important. So We have two types of lapis splice. What's the lapis splice? Whenever you have rebar, the length of the rebar is limited. Then you want to continue that, so you have to put lap. Sometimes you're not using lap. We are connecting them with something else. I'm covering that in the lab. In this class, we are going with just lapis splice. Yeah, with lapis splice in the column, or whenever you have a beam, long beam, you have 200 feet beam. All the regular rebar are 60 feet. So you will go 60 and then it's done. Then you have to go another 60 and then another 60 to get to 200 feet. So you have two options. You can go, imagine you have 3 rebars, yeah? Or you have a mat, something like a lot of rebar. Just, I will go with few. If you are starting from one point and just lap them at one location, all of them at one location. The splice length means that put them on top of each other, or adjacent to each other, and tie them together. That's the meaning of lap. Yeah, that's a lapis splice length. So if you are doing something like this, you need to find LD for one of the rebar. What's the LD? Based on the straight bar development length. If it's epoxy coated, top bars, all those stuff. Yeah. Find that one, then times 1.3 and must be greater than 12 inches. We call this class B. That's class B. You need longer splice because you cut all the rebar at one location. So we will add the longer the splice length to cover that problem that we cut them all at one location. But that's class B. That's the critical class. Yeah. So in this case, find LD for 1 times 30% more. Must be greater than 12 inches. That's your lapis splice. If you're going with one here, another back here, another back there, play with the location. You will be in class B. So you don't need to increase the development length 30%. Just calculate development length should be greater than that 12 inches. That's yeah. So as you can see, it's not that hard. And for the, you can use that for the column intention when you have column intention, and for the spiral, I wrote that this stuff here. You don't need to remember this stuff. Yeah, you don't need 48 times of dB. You have to put them on top of each other and then continue for the spiral. If it's a epoxy coated, 72 times of diameter of this bar, not the main bar, the spiral bar. Yeah, you can see the main important part is here. You need this in the field a lot. Yeah, please pay attention as your note. So we are done with that actually part. We are done. And that's for your exam up to there. This part is not part of your exam. From this part is not. Okay. Any question on the lapis splice?
A bit of that will be covered on the exam.
Yeah, it might be, but it's just you should know the load. If I ask you, we have class B splice number 8, calculate the development, calculate the length of the splice. No,
Okay.
it's yeah.
What is
Okay,
epoxy
for the
coated?
column. If it's epoxy coated, it doesn't matter. If it's epoxy coated, it will act on the LD. Can you remember LD has that epoxy coat with no epoxy coat or with epoxy coated? It will be act on this one. You don't need to consider that here. Just find LD times 1.3 or without any factor. Is that clear?
Yeah. Thank
Okay.
you.
Oh. So axial for axial compression means columns. We have actually round columns or square columns. Yeah, I showed that some pictures. So far you actually familiar with all these stuff. And as you can see, beams, all these tie bars. Look at this. How many tie bars do we have? Yeah. So it's hard to install these stuff sometimes. A lot of rebar. And then we have to make sure the concrete can get in. Otherwise, at the end, you will get a cavity. Nobody can see that. In earthquake, the earthquake can see those. We cannot, but earthquake can see. Yeah. So we must do something that we can see the problem as well before the earthquake find it. When earthquake find the problem, that's the end of that structure. If we find it, we can fix it. Okay, so these are just some pictures. And how can we capacity for axial load only? That's the equation. That's the equation. Pn nominal, phi Pn ultimate. Based on the material, this is provided. Yeah. So for the concrete part, 0.85 F prime C. Ag means, look at this, Ag column B times H, whatever it is. H doesn't mean that the longer side. No, just I call them B and H. So Ag, gross cross-sectional area of the concrete. That's Ag. B times H. Yeah. So Ag minus AS. AST what? Total rebar, vertical rebar that we use in the column. Total vertical rebar. We use 4 number 9. 9 is 1 square inches. 4 number 9 means 4 square inches. That's your AS. We use 8 number 8. 8 is 0.79 square inches. 8 times 0.79 square inches is your AS. AG is 15 by 20. So AG is 15 by 20 minus 8 times 0.79. Yeah, that's it. Fy times AST, AST 8 number 8, 8 times 0.79. Whatever you have. Yeah. So these are the equation, the same. If you are using a spirally, your phi is 0.75. If you are using tie bar, your phi is 0.65. Yeah, that's the things that actually we know from the start. Forget about this part. This is just part of your knowledge for spirally. Spirally is not that actually think that you need them a lot. Sometimes maybe in some structures, those are not actually that strong enough for earthquake. And the rebar, you need more rebar. And in column, when I'm going to the chart, I will talk about those stuff more. So this is the only part that from this slide, and you can understand concrete strength plus steel strength. This one, because I consider that steel strength, we are not going to consider that twice because we consider the whole area, but some part of that is rebar area. We deduct that. Yeah, sometimes they are not deducting that even. Yeah, if the rebar is not that big and the size of the column is big, so you don't need to consider that part. But this is the equation that you can always use. And transverse rebar. Transverse rebar reinforcement, we call that tie bar for the columns. Yeah, tie bars. Okay, tie bars. If you have just 4, that's it. If you have a spacing between the rebar less than 6 inch, every other one can be at the corner of each corner of the tie bar. If it's greater than 6 inch, a spacing is considered you have 8 inch, 8 inch, 8 inch, 8 inch. So each one must be at the corner of tie bar. So we have one closed tie bar, and then just single tie bars, single tie. Look at this. It should be 135 both sides. The confined area of the concrete inside. The rest in earthquake, we will lose it. This cover after huge earthquake, it will be gone. We don't have it. So this tail is 90 degree, should be on the air. And it cannot hold this like the other side that it went inside the concrete that will stay in because of the tie bars. But installation is not easy. Because of that, code will help us go with 135 from this side. Look at this, 135. 135 means 45 from other side. 135, and the other side, 90 degree. It's easy to install. Go here, install this, pull it back, push it in. That's it. If both sides are 135, you can install them. But the code asks, okay, you will install this, for example, 90 degree here. For this layer, 90 degrees should be the opposite side. Yeah. So 90 degree here for the top layer, 90 degree there, 135 here. For other side too, 135 here, 90 here. The upper layer, 135 here, 90 there. That's the code. If you go to the field and you see that they didn't follow that, stop them, talk to the design, the field engineer or for with that foreman and let them know it's not acceptable, change them. Yeah. You as a designer or as an inspector, you can follow these stuff, and those are very important in earthquake, and it can change a lot in a major earthquake. If we lose this part, the rebar can buckle. So the tie bars can stop this buckling. If the tie bars are too far and they didn't install them correctly, then you will lose the confined area. Look at this. We lost the concrete inside. If you lose it, you will lose the column. If you lose the cover outside after huge earthquake and the rest stay intact, you got it. The column could tolerate the lateral earthquake, and it should be okay. So these are the rules for every other one, and I showed that you can go with single. Look at this. If you have two this side, 190 degree here, it one layer, 135, 40 on the top layer, 90 degree here, 35 here, 90 here. Yeah, you have to just change them in the row and in the height. You must do that. What's the tie bar spacing? This is the maximum tie bar spacing. So you shouldn't go more than this. Less than this, you can. So should be minimum of this 16 times of diameter of the main bar. This is the main bar. 16 times of that. 48 times of the diameter of the tie bar. Or a smallest size of the column. So you have 12 inch, 30 inch, 12 inch. So this one is 12. Then calculate them. Minimum of these three is your maximum spacing. Maximum. You can go less than this, not more than that. Any question on that? Okay. So far, I gave you compression only. If we have moment, then what can we do? Not that hard. It's very easy. Column up to here is easy. With the earthquake and slender column, then you have to do something extra. But otherwise, it should be very easy. That's the elevation view. I cut the column. Column is high to the footing or whatever. We have point load plus moment. So I can show this as actually eccentric load like P, and this arm should be M divided by P. So E times P will give you moment. You can transfer this to here, and then E times P, your moment, you will get the same as this. Yeah, you can show it like this or like that or like this. They are the same. Pn is the nominal axial load capacity with this eccentricity. So I can show this like this. These are the rebar. If I have moment up top, and just remember B. B is always B in this case. What's the B? B is the side of the column parallel to the eccentricity. The other side is H. Doesn't matter if it's bigger than this or a smaller. Always B, remember this. Always B must be parallel to E. So let me do some practice. So assume that this is your column. Okay. If your E is here, I'm showing this plan view. So the point load is here. And that's your E. So which one is B, 1 or 2? That's a plan view. That's elevation view. So that's the load with this eccentricity. Which one is your B, 1 or 2?
Would it be, did you say parallel to?
Must be parallel to E. This is E. So which one is your B?
1.
1. Yeah, 1. H is always perpendicular to E. So this is B, the other one should be H. So this one, let me go with this. Load is here. Yeah, and this is your eccentricity to the center. Which one is your B, 1 or 2?
2.
2, parallel to E. This is your E. Look at this. That's the point load. Eccentricity to the center of the column, like this one. Eccentricity to the center. Yeah. This is elevation view. This is the plan view. Is that clear for everybody?
Yeah.
So B is always parallel to.
Always parallel to E. That's it. This side is parallel to E, B. This side is parallel to E, B. So this is B, this is B. The other side should be H. So B or H can be changed. Yeah, doesn't matter if it's a bigger or a smaller. It's not the things that we separate B and H. Parallel or perpendicular to E, B and H. Okay, so let me, okay. So when you have moment, you will get compression at one side, tension other side. And you have, look at this, when you have moment, point load here, it means you have moment this side, compression here, tension there. Okay, so these are the tension bar, that's the compression bar. And we have compression concrete as well. Yeah, and we know that this is your actually the dimensions that you can consider in this case. So your 0.85 F prime C, A prime S times, that's the rebar that you have. A prime S still in compression times F prime S. That's it. So distance from A, look at this, that's the distance A. A is that compression concrete block, like beam. Yeah, if you rotate this direction 90 degrees, it should be like a beam. Yeah, so from center to the back side of this is H over 2. From here to here is H over 2, if we call this H. Yeah, so if we call that H, that's your H over 2 from here to here. So from here to this distance should be H over 2 minus A over 2. Yeah, this is A over 2. Total A, like here, and this is the center line of A. So center line of A over 2. That's the center of total, H over 2. So distance between these two should be H2 minus A2. That's it. What's the distance? A prime S to the center. A prime S to the center, you can see H over 2 minus D prime. We have D prime to the compression bar. So H over 2 minus that one. What's the distance from here to your tension bar? D from here to the top minus H over 2. Yeah, you can see everything here. If you follow, you cannot actually make a mistake. Those are the distances that we have. So if we write sigma Fy equals 0, so everything upward positive, I consider this direction. Okay, so we have Pn downward negative. Then 0.85 F prime C times A times B, other side, total compression volume of the concrete, plus F prime S, A prime S, yeah, minus AS F prime S. So if you write this and rewrite this, actually push Pn to other side and then keep the rest at the other side of that equation, you will get this. Pn should be total compression, compression bar total force, concrete force, concrete pressure, compression total force, and negative tension part. That's your Pn. And then if I write sigma moment around Cl, around here, yeah, That's the equation. Mn, nominal moment capacity for this column, is Pn times E. Pn times this distance equal compression of the concrete, 0.85 from C AB, like this one, times distance from center of this A block to here, H over 2 minus A over 2, plus A prime F prime S times distance from here to here, H over 2 minus D prime. Then AS FS up to here times this distance, D minus H over. That's a, if you follow this check, this actually stuff on this here, you can find stuff yourself. So we have Pn and Mn. So Pn and Mn, those are the for any location that you can find the capacity, moment capacity, and the axial load capacity, and these are from the beam. Yeah, based on distance d prime, d epsilon. That's the strain diagram. Epsilon u, that's for the concrete in compression. Epsilon prime s means from here to here, means the strain in compression bar. And this is here on the rebar side, that's the epsilon s tension rebar strain. And relation between all those, these are not new. These are exactly from the beam. Yeah, we know this from the beam. So whenever epsilon for the concrete, yeah, is epsilon u, means reach to 0.003, and epsilon s for tension is equal Fy, we call that balanced failure. It means that concrete and the bar will reach to the yield at the same time. We call that balance. So C that we can calculate from any of these equations at that point should be CB. So instead of S on that equation, we instead of over here, if I change that with epsilon y and rewrite this based on C, that's the equation. Yeah, so I can call that CB for the balance point when epsilon C is equal to epsilon U and epsilon S is equal to epsilon Y. That's the balance point. And balance point is this point. When your actually your C is less than C balance, your C is less than C balance, you are in tension region. This part is tension, that's the compression region. What's this shape for? This shape will show us relation between Pn and Mn and the capacity of your column. So when there is no moment, yeah, moment is 0. So it's just a full column, yeah, pure column. It has just Pn. If there is no axial load, you have just moment, Mn. It's just pure beam, yeah, pure beam, Mn only, pure column, and between these two, beam column, because it has force, axial force like column, and moment like beam column. Yeah, that's the diagram. Later, I will go through this a lot, so you will learn all this stuff, how to calculate this. And this is example, I think it's a little late for this one. I think we'll go through this next week before exam. We have a short class and then we have our exam. So I go after this part in that class. So that's it for tonight. And after this we have lab. Please, those that they have lab, don't go, stay, and just I have to do something to add your name to the lab, and after when you are in the class, please stay there. I want to see your name, and then as soon as I'm done, it will take a few minutes, then we can start our lab, and I can let you go sooner. I think it's better. I talked to you last week and everybody was happier with this system. So any question on today class?
This is more about the lab today, so we're starting immediately then?
About few minutes.
Okay, how many would you say?
Just, yeah, about maybe 5 minutes.
Okay.
Yeah, but please do not leave. Those that they are done and they have no question, you are welcome, you can go. And the rest that they have left, please stay. And after 5 minutes, start. Okay. Which lecture are exactly going to be on the test? I think I told you on the start. I told you on the start. Everything from exam 1 all the way to B4 column. Column is not part of the exam. So from everything after exam 1 all the way to B4 column that I covered today. Lapis splice and those cutoff point, those are part of the exam, but the column is not. Clear?